Hi and welcome to our next webinar. Today's webinar, another topic, same, but still a little bit different. The topic is same, but different. Today we're not going to talk about Pacton. Today we're going to talk about our product, our own lithium disilicate, Livento Soprano. And it's my pleasure to welcome Kai from Zurich. He's gonna speak about our fantastic material. So, hello to Zurich, Kai.
Hello, Marco. But you have stopped my camera. You have to activate it again.
Okay, we're gonna ask to start video. As you can see.
All right.
So there we are. Hi, Kai. Hello.
Hello.
Kai is one of our key opinion leaders about the material. And I have to say, if someone really did some scientific work and comparing apples with apples, it's definitely Kai. So Kai did a very big job, and I'm sure you're gonna blow us all away. Mind-blowing presentation. So I'm looking forward to this presentation. Let's go, Kai. Good luck.
I will try my best. Thank you.
Thank you.
Hello to everyone. Hello to everyone else. So let's start. Livento Soprano. But first of all, little introduction to myself. I've seen there's some people already in the room that know me already. But for all the other people who don't know me, like I was born and raised in Germany, and after my education, I went to US for 2 years, and since 2009, I'm living in Switzerland, and it's my big pleasure to announce the opening of my own laboratory, NML Dental Manufactory, in April this year. Unfortunately, it was a little bit of a rocky start, but now everything is opening up again. It looks pretty much good. So here's a little introduction of my laboratory. Everything is very new and I'm very proud of it, but that shouldn't be the topic of today. Always when I need some inspiration for when I don't know what I want to talk about, or when I need some inspiration for my work, I like to visit one of my best friends. That's Steven, and Steven is a chef. And Steven is quite an extreme chef because he is growing all of his products he's using in the kitchen by himself in his own garden. Or when he's using mushrooms, he's going to harvest the mushroom in the forest. So he's quite an extreme character, but he's also a very creative character. So always when I need some inspiration, I like to go to his kitchen and have a chat. And so when the people from CM asked me if I can do a presentation for them on Livento Soprano, I didn't really know what to talk about. So I went to his kitchen and said, hey, Steven, can you give me an advice? Like, what's the most important thing for me to know, or what do you need to know for your work to make it perfect? And he said, well, for me, what's most important? That's easy. It's the ingredients. Because the ingredients are the base. And if I know the base, I'm pretty much free to do whatever I want to do. But what about your ingredients? Do you know your ingredients? I said, I don't really know. I have no idea. And that's when I started my research about lithium disilicate. And so please come and join me today when we visit the molecular kitchen of inorganic chemistry, where we'll try to explain you what every type of ingredient we find in lithium disilicate means and what their job is. So here's our dish of today, or our menu, lithium disilicate. But what's inside? is actually much, much bigger. And I don't know, like if you still know all the chemical words for it, but like I needed to do some research for it. And so inside we find silicon dioxide, lithium oxide, zinc oxide, potassium oxide, sodium dioxide, phosphorus pentoxide, zirconium dioxide, aluminium oxide, and lanthanum oxide. And now I want to show you, like step by step, what the job of each ingredient is. So let's start with silicon dioxide. Silicon dioxide, most of you guys probably know as quartz. It's very hard to melt, like the melting temperature is over 2000 degrees. So it has to be mixed with some other materials like boron trioxide or sodium dioxide to decrease the melting temperature. And this builds the highly amorph glass matrix. Lithium oxide is a so-called nucleation starter. These are tiny bits in the melted ceramic where the crystals can start growing. And these build and strengthen the whole crystal structure. So we can see already that silicon dioxide and lithium oxide build the so-called main structure, and all the other ingredients are the so-called modifiers. And these modifiers make a difference. For example, if you're having an Evoclar Emax or a GCDC, or in our case, Livento and Soprano. Zinc oxide is used in lithium disilicate to decrease the chemical solubility, because as some of you guys at least know, that any kind of like inorganic material is soluble in a moist environment. So, but we have to be careful also about this, because too much of zinc oxide enhances the resilience of the material, but also decreases the flexural strength. So we cannot just put a huge amount of zinc oxide inside to decrease the chemical solubility, because we will weaken our material. And new studies show that zinc oxide also has an antibacterial effect in glass ceramics. Potassium oxide we find in our material for homogenizing our melting behavior, but it also has the highest influence of the coefficient of thermal expansion. Plus, it also enhances the refraction index in glasses. Sodium dioxide, in our case, is really used to decrease the melting temperature. But also here we have to be careful, because if we have a high amount of sodium dioxide inside, it destroys the glass structure. So it makes our material too weak. Phosphorus pentoxide is a very difficult word, and I had to do a lot of research about it because it's a very unknown material. In our case here, it is used to also for a heterogeneous nucleation. That means that all crystals can lay separate and intervene with each other, but they are not melting together, so they can really build ash. And what you have to maybe remember for later on, it builds a so-called beta quartz. Some people also call it a glass in glass. This, please remember, like we come to this later. It's quite interesting material. Zirconium dioxide is used in lithium disilicate to enhance the immediate flexural strength, and it is also has the main job for good grindability, and we can also have a nice, much nicer polished surface afterwards. And they are so-called ZLS ceramics. They have a higher amount of 10% of zirconium dioxide inside. Aluminium oxide enhances the tensile modulus, so it's used for framework reinforcement. And it also simplifies the ionic bond of rare earth elements. And this is also like a key point, because the rare earth elements are have the job to have like to keep the luminosity in our material. So without aluminum oxide, like we will get very gray crowns. Lanthanum oxide, I put it in hyphens because just one manufacturer is using lanthanum oxide at the moment. It is not really necessary to have it inside anymore, like it used to be. It used to be necessary, but with some more research, other manufacturers found that they are actually much better materials instead of lanthanum oxide, because you have to know lanthanum oxide has a quite a high radioactive emission. Nevertheless, lanthanum oxide is used as a reinforcement agent. It's also decreasing chromatic aberrations. That's why the old, very old, like camera lenses and so on, were all lanthanum glasses. So it has like a very good lightability, but it also has some big minus points. Better materials instead of lanthanum oxide, in my opinion, is, for example, yttrium oxide. You guys know this from zirconia. It's also used as a framework reinforcement, but in lithium oxide, lithium disilicate, it also enhances the fluorescence. So, and this is quite interesting for us. Other possible components could be titanium dioxide, also as a framework reinforcement, boron trioxide as a bonding agent, magnesium oxide, as well as a framework reinforcement, or calcium oxide. So, and here I gave you all the ingredients like split up in their properties, so you guys can see that like each material has more than one property in the whole material. So for example, zinc oxide is used for strengthening the material, but as well used to control the melting temperature. And it's used to build the glass matrix. So, and there you have to be careful, because it's like with some medications, like that they are not working against each other. One property is still missing. It's the color. Like we know some materials already is lithium oxide, phosphorus pentoxide, aluminium oxide, and big question mark. And I will come to this later. Okay, so now we know our ingredients. Let's start cooking. Let's start with the preparation. Let's build lithium disilicate. And these are the 5 stages of lithium disilicate till the final stage, stage E. So we have all our ingredients. We mix them together, we melt them, we cool them down, and we grind them. And lithium oxide crystals start growing. That's what you see in picture A. After another melting process and cooling process, these crystals already start growing to so-called submicron elongated crystals. These 2 stages are called so-called amber phases, because this glass which is built there is really kind of deep yellow brownish color. This color changes after the next melting and grinding process. It changes into the so-called blue phase, where we find the colonies of elongated crystals, and you guys probably know this as blue ceram from Ivoclar. And with this double sintering process, like the crystal structure is finalized to the last stage. In our case, for our press material, we get the stage 4 in press ingots in the so-called layered colonies, and we change into the last phase in the highly intertwined colonies with the pressing process. So it's very crucial, and never judge the color and translucency of the final restoration with the ingot, because during the pressing process, the translucency and the color is changing. So, plus also the stability. And I know you guys know this already, but I say it nevertheless, never use pressed plunger or the pressed ingot to press something again, also not as like an extra reservoir, because the final stage is already achieved and no one can really tell what's happening after the final stage. So like if we press it again, like these crystals, they start melting together, it's not stable anymore. They are changing colors, they are changing translucencies. No one can tell what's happening. So, but some of you guys might ask, yeah, well, what's the difference of these different materials? And it's a good question. And one of my colleagues here in Zurich gave me the answer. Well, everything is the same. And I showed him this picture. So, well, this is also, everything is the same. Everything is cheese. Everything is made from milk. Everything comes from the cow. Everything is coming from Switzerland. But don't tell Swiss people that all of these three types of cheeses are the same. And so he understood what I meant. One of the differences, for example, could be the crystal sizes. Like here on figure 3A, you see disilicate before pressing, and on figure 3B after pressing. On figure 4A after pressing. And on figure 3B, you see Emax before pressing, and on figure 4B after pressing. So you see there are quite big differences on crystal sizes, and they have a big impact on the flowability during the pressing process, on the durability, and of course of the cross linkage, because you have to understand that between the bigger crystals, there is much more space for the single glass structure. And this glass structure itself is not so stable. It's just in combination with the lithium oxide crystals we can get the stability. So if we have a more compact crystal structure, the higher stability we have. And also the refraction rate of our material is much higher. So we don't get any gray crowns. And also the numbers show this, that the intermediate crystal sizes of Emax, for example, are between 3 to 6 micron, and disilicate as well as Livento press are between 2.2 to 2.6 microns, so they are half the size. So we have much more dense material. Another difference is the glass matrix, and also this has an impact on the flowability of the process, on the durability, and very important on the color accuracy. And I will show you what this means later. So let's start about color. In my courses, I always ask you guys, you know how colors are created. And often I get the answer, yeah, colors are created by metal oxides in ceramics. And this is true if we talk about classic feldspathic ceramics. But we are not talking about PFMs today. We are talking about synthetic ceramics. We're talking about full ceramics. And I never heard this word before until I met Robert 2 years ago. And Robert told me, you know, like colors for lithium disilicate in modern synthetic ceramics are built with so-called doped glasses. And I never heard of this before. And I asked him, so tell me, what are doped glasses? But he told me, yeah, you have to learn for yourself. Here, read some papers, do the research for yourself. And I was looking for many hours, for days, and it was almost impossible. So in the end, I just typed it in, doped glasses, Google picture search, because I'm a very visible guy. I need pictures to get some imagination. And that was the first picture I found. And it looked very complicated to me, but also somehow some little bit scientific. So I tried to make a point out of it, because we can see like on the left side, so and so much energy gives so and so much wavelength on the right side. So it has to do something with colors, right? But today I know that this is so-called radio frequency transmission. And you guys probably have seen this or have been tested like this at the airport. Maybe not now at the moment, but maybe at your last vacation when you came back home. So that's when you guys go to the security check and you are checked for explosives. Like that's the graph that comes out from this machine where they check for explosives, because every material has their own light emission. So I didn't find really that this has something to do with doped glasses, but it was a good try. After a while I found, oh, actually I have a friend who is a physicist, so maybe I know he can give me the answer. And that's him, that's Nick. And you guys see, like he has a really crazy laboratory, and I called him up and said, hey Nick, I have a question, like I want to learn about doped glasses. Have you ever heard of it? And he said, oh yes, of course. You know, like I'm doing research in diamonds, and I want to grow artificial diamonds. And for this, I'm also using doped glasses. I said, wow, that's great. So please explain me. And he says, like, how you do it? And he said, yeah, you know, like here and there, blah, 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 blah. But it was way too complicated for me, because I'm not a physicist, I'm a dental technician. So I said, so does a machine do it? Is there a machine? Do you have a picture? No, like I want to have some imagination. He said, yep, like there's a machine. And the process we are doing is called molecular beam epitaxy. Wow, yeah, that looks cool, but I still don't understand. He said, well, yeah, no problem. I sent you another picture. Maybe here it's easier for you to understand. So just imagine, like in all of these like orange containers, there are metal oxides inside, and they are heated with a plasma source. And because this plasma source is so hot, the metal oxides, they steam off, and they can be attached on a substrate. I said, okay, yeah, like I can imagine now, that makes sense. And it's a very precise process. You know, you can do it on a molecular level. It's very clean. Until he said, but this works for his diamonds. This works also for astronomical mirrors. They have to be so precise. They have to be so clean. But for your material, this process is maybe a little bit too expensive, because like our ingots would cost maybe like 300 to 400 euros or dollars each. So I'm very sorry, but this is not Star Trek. Fact is, the doped glass is already in the melted material inside. So how did it come inside? To understand, like first we have to understand how an ion bond works. And I don't know about you guys, but like physics and chemistry was not my favorite subject in school. So, but I had to learn it again. But it's not so difficult. So I will show you guys. So what's the most simple crystal structure one can imagine? It's sea salt, right? So let's take this as an example. So we have sodium and chloride. Sodium has 11 protons. Chloride has 17 protons, but this is not important for you guys to remember. What I should remember are the electronic shells, like from the Niels Bohr shell example. And also Professor Bohr explained that there's the rule of 8, which means that every shell of every atom can host up to 8 electrons. If there are more than 8 electrons in one shell, another shell is created. If there are less than 1 electron in the shell, like the shell is decreased. And we also have to understand that every atom wants to have a full shell. Because like with a full shell, they are least reactive than with empty shells. So let's see what happens when sodium and chloride meet. They can see each other. Chloride has 7 electrons on the most outer shell. Sodium has 1 electron on the most outer shell. Chloride wants to have a full outer shell. So it tells sodium, hey, why don't you give me your single electron from the outer shell so I get a full outer shell? Your most outer shell is decreased, but you also have a full outer shell now, and we can become best friends. That's how an ionic bond works. And if you now understand how an ionic bond works, you also can understand how ionic doping works. We are coming back to our phosphorus pentoxide. When I told you that you have to remember this material and the glass-in-glass method, or the so-called beta quartz method. Because on the most outer electrons of this material, you see there's some so-called double oxygen bindings. And on these double oxygen bindings, metal ions can be attached. And these metal ions, they change the color properties of our material. So we are not talking about physical objects anymore. We are talking about electric tensions because we are changing the electronic tension of the molecules. And with this, like, the whole color appearance changes. And this is, of course, very interesting because since they are not physical objects anymore, they cannot sink to the core like with our PFM ceramics. When we fire them like for the third, for the fourth time, the ceramics, they change into some grayish hue. But the reason is because like all the colors or the oxides, they always sink more and more and more to the core. And what's left on the outside is the pure glass face. This doesn't happen with these kind of modern synthetic ceramics because we are not talking about physical objects of color anymore. We are just talking about electric charged particles. So we see on the wheel of properties, color moves into the core, and color is created of lithium oxide, phosphorus pentoxide, aluminum oxides, and metal ions. Here are some examples of what these metal ions can give you the color. Like I want to tell one special one of these because I don't know if you guys know about the difference of feldspars. Like the classic PFM feldspars or Kali feldspars, like let's say creation, Willy Geller creation. And Mr. Geller's idea for creation was that he wants to have a Kali feldspar because Kali feldspar is very clear. It doesn't have any kind of color abbreviations. So, but this doesn't work for synthetic ceramics because Kali feldspar is very hard to melt. Like you guys know, as PFM ceramics, they kind of melt, or like we fire them over 900 degrees. So this doesn't work. So we use, instead of Kali feldspar, we we use other feldspars, and they kind of tend to have a greenish hue. So like we never get the real original color, a really clear glass. But what the scientists found out is like if they attach manganese ion 4, like this greenish hue can be removed and we get a clear glass face. And we can also attach, of course, ions of rare earth elements to enhance our opalescence and fluorescence. So that's so far for the ingredients, but now really let's come to the difference of materials. Like what are the differences of, let's say, an Emacs to a GC to a Livento to so many products. So I made a in-lab research for myself because, of course, like I want to work with the best material there is on the market, right? So let's start. You guys see here the 7 colored circles, and each circle stands for one product from one manufacturer. And from each product of each manufacturer, I made 15 specimens, and I measured and calculated them with an approximately deviation of 10%. So first I looked at the manuals, and I found the difference, flexural strength higher than 87 megapascals. And that's very high. Like, I mean, we are talking about immediate flexural strengths of, let's say, 400 megapascal. So this is almost a difference of a quarter. That's a lot. I also found quite many differences in the investments they are providing. So we find some that are extremely inviscid, some are quite thick, some are finely grained, some are coarse. Like one was very difficult to mix, like the color and the powder and the liquid, they always kind of demixed. Some were very porous. Like everyone had a different idea. I also found a very big difference in the pressing temperature. I mean, like higher than 43 degrees, and a big difference in pressing times, 17 minutes. And that's quite a lot. Here you see the reaction layer after the divestment. And you guys have to understand, like everything was sandblasted with 2 bar aluminum oxide for 1 minute, except for the red specimen, because the manufacturer asked to just sandblast it with glass. But you guys can see, like there's already quite big difference. And the reason for the reaction layer is that, or like how we can inhibit this reaction layer is aluminum oxide in the investment. Some manufacturers also give like a liquid to spray on the wax pattern, and this is just liquefied aluminum oxide. But with this, we also have to be it's quite difficult to handle because we have to spray in a certain distance and just spray once. So like we can do many mistakes. So in my opinion, it's much better to have it directly in the investment inside. And you guys can see like some manufacturers have higher amounts of aluminum oxide inside, some completely nothing. I also found a difference in firing temperature of the first and second dentin fire higher than 57 degrees. So it's also quite a big difference. But now let's go to the biggest differences, and that's color. I measured the color with the ELAB protocol, and I guess like all of you guys have probably heard of the ELAB protocol from Sascha Hein and the bioemulation group, so I don't have to explain how ELAB protocol works. But it's a very good tool also to compare like colors in the laboratory, because we don't have any photospectrometers normally in the laboratory. What does the LAV stands for? L stands for the luminosity, A stands for the red value, and B stands for the yellow value. And with this, we can describe all the three characteristics where we can describe every kind of tooth color. With these LAV values, we can also describe and calculate delta E's, the difference of two colors. And we have to understand that like everything below delta E of 2.0, we cannot really see a difference. However, everything that's higher than 2.0 of delta E, we can see a small to a high difference in color. It's a reference color. I used the mathematical or digital color from Sasha, which references to an A2, because as most of you guys know that the shade tabs we use in the laboratory or in the dental office, like even if they are from the same manufacturer, they all have quite big differences. Like here as an example, I used the Vitalumine Classic A2, and you guys can see like they all have quite a big difference. Like the left to the middle one has delta E of 4.96, and also the right to the left one has a delta E of 2.02, and even the one that comes closest to the digital reference, which is the left one, still has a difference of a delta E of 1.64. So it's not visible, but it's still quite measurable. These are the color of the press ingots after pressing of an LTA2 ingot. And I hope this Zoom meeting the quality is still good enough that you guys can see that these are not the same colors. The measurements also show that, for example, the green specimen has a very high value, or it seems like it has a very high value, but the orange one actually has a much higher value. So, and if we compare this now with our reference color, we can see there are also very, very big differences, but some are also quite close already. I did the same with the veneering material. And also here, you guys can see like very big differences. So it seems like it's not so easy to produce a stable color. I mean, like, aren't we talking about color standards? Here as well, the delta E's show quite big differences. And why is that? And I was really puzzled. Then I got another idea. So how stable are these colors and values after several fires? So the number block you see stands for 15 specimens. And after every fire, I measured these 50 specimens, took the mean value and compared it with the first fire again and again and again and again. And after they exceeded the delta E, I kicked them out. So what you guys can see is the purple specimen lasted 3 fires until it reached the delta E of 2.0, until it got a visible color change. Some lasted 8 fires, 9 fires, and the turquoise specimen on the very right side just lasted 2 fires. I mean, like, we cannot even do a glaze fire, like first dentine and second dentine fire. No glaze fire anymore, or we will have a color change. So that's very important to know. But I was still puzzled about these big color differences and how manufacturers can say like everything will be an A2 in the end. So I got an idea, like I was using an LTA2 ingot. So, and this is normally used for a cutback technique. So my idea was, okay, probably like I will get this stable A2 color after I attach the veneering A2 onto the framework. But how can I do this? I mean, like I work in a dental laboratory, and how can I be so precise that I always have like the same veneering thickness on the same framework thickness? So I needed to find maybe a mathematical way, because we are talking here about 210 specimens. And this was quite difficult. So I went to the ETH University here in Zurich, which is the famous technical university in Switzerland. And I went to the Department of Computer Science and Electronics. And there's Professor Herzog. And I was having a chat with him, and I said, I want to compare colors like in a mathematical way. And he said, well, first of all, if you want to compare this, you have to consider about your translucency. So first we have to measure the translucency of your framework material, and we have to measure the translucency of your veneering material, because they interact with each other, of course. And he gave me first an equation to calculate this, but I'm not a mathematician, I'm not a physicist, I'm not a chemist, I'm a dental technician, so I need to do something with my hands. He said, well, that's also possible. So that's how I prepared the probes. Like here we have an example specimen of thickness of 0.5 millimeter, it's dentine A1. And he said, put this specimen on a perfect black background with in contact liquid. Take your ELAB picture and do the measurement. Take the same specimen on a perfect white background. Take your ELAB picture again and do the measurement. And just look at the L value. And now it's just a simple understanding. With a black background, our material is 55.2% away from perfect black. And it's 10.86% away from perfect white to 100% of L value. And now we just have to, now it's just simple math. And we get a translucency of 44.34%. I did this for all the materials, or for the layering dentin, and you see there are quite big differences of translucency of the dentin. And I don't know if you guys remember the red specimen from the veneering material. It was very dark, it seemed like, but actually it's not the question of chroma. It's more what we saw is that it's much more translucent than any other of the dentins. And now it got really, really complicated. I had to go back to the ETH because a calculator was not enough anymore, because we needed to calculate the dentin considering the translucency to add it onto the ingot. I was lucky enough to use some computers from Dr. Herzog, and he helped me a lot with it. So on the bottom, you see the final colors. These are just calculated colors, predictions of this adding. And now if we compare them with our digital color, you guys can see all the delta E's coming down. So my idea was right to have combined the framework, of course, with the veneering material. Like, numbers look much better all of a sudden. Everything is under delta E of 2, except for the turquoise specimen, which is still has a delta E of 2.71. But also one is standing out for a very good delta E, which is the yellow one. And why is that? It is because the L value is just 0.18% away from our reference color. It's also 0.18% away from our reference color in the A value. And the purple specimen is 0.02% away of our reference color. But the overall rate we have, the best rating we have from the yellow specimen. And just as a reminder for you guys, like everything under 2.0 is considered as the same color for human eye. And everything higher than 2 is like most humans see a color difference. And you guys can see like the yellow specimen is really no difference, even mathematical. So let's talk about fluorescence. I know like there's still quite big discussion like how, well, what's the influence of fluorescence in daylight, and how do humans really see fluorescence in daylight? Like Sasha Hein also showed in his study 2 years ago that like the human eye cannot detect fluorescence in daylight. But there is something about it. I cannot really say. What you guys can see here under the colored balls is like I took fluorescent pictures like of the ingots after the pressing process, and believe me, under the green and under the turquoise specimen, there are still some ingots to be seen. It is just like they are just the fluorescence at all. Anyway, let's compare it with some natural fluorescence. This picture I took from a dental assistant. She was 25 years old, so she has the highest fluorescence we find in humans. Her tooth shade, of course, was also A2. And now we can compare it, the natural fluorescence, with our materials. I took the LAB measurements again. I also took the LAB measurements of the ingot and as well the fluorescence LAB values of the veneer material. I did the same calculations as before. I add them onto each other. And also in fluorescence, we are just interested in the L value because it's just a question of luminosity, not about color. So now compare for yourself, like the differences and why is that? And surprise, surprise, the yellow specimen stands out again. Is it because the color is so precise? So these are all the tests I did in the laboratory. I know it was maybe quite a lot to take, but I hope I could give you a good overview picture of like what's out there on the market. And now still the question is like, for what did I decide, and for what will you decide? And I want to ask Marco, maybe you can open the microphone of everyone, or like maybe all guys who are listening, you guys can open the microphone and maybe say like what would you have picked?
Kai, I would recommend
Yes.
there is a possibility to raise the hands, so you can
Okay.
for example, ask who would decide for purple, whatever, and then we can see about raising the raised hands, right?
Exactly, yeah, like guys, raise your hand for purple. Who would have picked purple? Marco, can you see it? Because I cannot see it.
There are no hands.
Hands, okay. Who would have picked green? No one?
Maybe you can see in the menu bar below on the bottom of your screen, there should be this ability to raise the hand, right?
I don't see it. Very sorry. Well, anyway, who would have picked yellow?
Probably everyone.
Yeah, everyone. Who would have
I
picked
see
red?
4 hands. I see 4 hands.
Four hands for yellow. Okay.
3 hands.
Who would have picked red?
So you have to. Yep. So 2 are on the red side.
Okay. Who would have picked blue?
2.
2. Who would have picked orange?
Again 2.
And who would have picked turquoise?
Just 1.
Okay. So conclusion and like what did I pick? I picked yellow. And this is Livento Press Soprano. So, but like this was all very theoretical, right? But most interesting, of course, for us is like to see the material in the mouth, like when it works for the patient, right? And when it's reliable for us to use, like we have easy work, like we know what to do, and we know it's not changing also after, like if we have to do another fire. So like we come to the end of the menu, like we come to the wrap up, to the dessert, and I guess for all of us technicians, like the nicest time for us is like to see our work in the patient's mouth. I just want to share with you guys some of my cases from the latest time at the moment. So this was the shape match I took, and there was at try-in, I did tooth number 22 on the right side. And now, guys, I can tell you, like, this is monolithic, just stain and glaze. And I was very happy about it. This picture, the provisionals on it already, unfortunately. I did central, color match, and with a try-in, and after cementation. And here it got a little bit more complicated. So like this patient wanted to have a new cantilever bridge and a new crown, but he was also not very happy with his centrals. And also the canine on the other side, he was not happy with the color and the shape. So he wanted to have 3 additional veneers. And it was quite challenging because like we found that like on the 2 centrals there was quite big cavities under the gum and in between the teeth. So we needed to do some kind of hybrid crown veneer things. So the question of ingot was also quite a challenge. But like the stability of value of Livento Soprano helped me a lot to achieve this case. And also with the double polarization filter, we see that like the color is very stable also to the natural color. And even under fluorescence light, like we see like it has a very natural appearance. We can also do some very minimal invasive cases with it. Like this one, I just used Soprano 10, no framework underneath. I just did it on platinum foil. With the shade matching, I also asked the patients if he's okay if I do these kind of enamel effects inside the incisal area, and he said yes, of course. Like he wants to have very natural appearance, and he's also quite sure that he had it before his accident. So, like I could achieve also these highlights inside, and these are not stained. Like they are really layered inside, as you can see from the side pictures. And of course, we can also have a little bit fun with the materials. We can just layer teeth for fun. And I want to ask you guys if there are any more questions.
So, hello from my side. Thank you very much, Kai. Awesome presentation. As I warned you before, it's mind-blowing. I guess there is such a huge work behind of this this amazing presentation. Thank you very much, Kai, for sharing your experience and congratulations.
Thank you, guys.
Research work. So, I would say if there are any questions so far right now, you can raise your hand. I will ask you to, or allow you to talk, and you can directly ask Kai your question by your person. So, are there any questions? Yes, there is there's a question from Mark. Mark, please switch on your mic.
Morning.
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 What investment do you use?
I use the original investment from Livento Soprano. It's called Livento. Livento Press, exactly. And like I also did some cross testings with it. So like the Livento investment with, let's say, Emacs or GCDC, and I always got the best results with Livento Invest. It's
Excellent.
very stable. It's very stable. It has no reaction layer, and like it's so stable, you can even use it for refractory dyes.
Yeah. Thank you.
Okay. More than welcome.
Thank you, Mark, for your question. More questions? Doesn't look like, so we are just in time.
Look like.
If there are any more questions, so you can send them directly to Kai. You can also, there is another one. One more.
Hey.
A question from Novat. So you're allowed to unmute.
Yep.
Okay.
Hi.
Hi.
Hello.
May I know what is the best milling on Picton? Is it wet or dry for milling?
I would say this is another topic.
I'm sorry for that. because we're using the Picton
no problem.
I guess.
You're talking also to a Pecton specialist here. I would recommend to do it. It doesn't matter. In fact, it doesn't matter. You can do it wet or dry. If you are doing with dry, just to ensure that you lower the speed, and otherwise it melts the material. If you do it underwater or on the wet, you don't have the problem with cleaning up of your equipment because of a static load of the flakes, and they stick everywhere. Okay.
Right. Yep. Thank you very much. I appreciate it.
Thank you.
Thank you.
Any more questions? So otherwise, ask directly to Kai. You can also send us your questions. Also, your feedback is very, very welcome.
Exactly.
You can send us your email to the address cmsa.ch. Now, many C's in there. So, okay. So
yes, and also
otherwise,
like if there are any questions directly to me, but if they come up later, like Marco can forward these questions by email to me as well. So no problem.
for sure. Also, if there is any feedback, always welcome. Otherwise, thanks again, Kai, for sharing your presentation. Again, fantastic presentation. Also very, very nice designed, very nice pictures. And
Thank you, thank you.
thank you to all the attendees for taking part, for being with us on air. And
Yes,
see you hopefully next week again, same time, same day, another date, same, but different. Yeah, it was great having you here in our webinar. So thank you, and stay healthy. Have a great one. Bye bye, everyone.